Hey everyone, welcome back and let's write some more neat code today. So today let's solve word search 2. And once again, like usual, this is a problem from the blind 75 Leetcode list, a list that we have been tracking on this spreadsheet, and the link will be in the description to this. And we are very close actually to being done with all the major problems on this list that I wanted to do. And probably at some point I will finish up some of these easy ones like contains duplicates. I think that's a pretty trivial problem. Don't know how many people are waiting for a solution on that one, but I probably will do it eventually, just for the sake of completeness. So this is word search 2, and word search 1 actually we already solved on this channel, and that is Leetcode 79. So I do recommend understanding that problem before you try to do this one, because this is definitely an extension of that one. So we're given an M by N board exactly the same as we were in word search 1, and we are given a list of words this time. Previously we were just given a single word, but in this case we're given a list of words. And we want to know from that list of words, which of those words exist in this board, and whichever ones do exist, we want to return those words. So previously, we only wanted to know if one word existed in here or not. So we returned true or false. But in this case, we want to know how many or exactly which of these words do exist. So if we just reuse our solution from the first word search, what we're going to do is we're going to go to every single position in this grid, and we're going to start a depth first search recursively on here. So it's just backtracking, right? We're going to be checking brute force. What's every word we could come up with, right? So starting at O, could we come up with a word in our list of words, right? So we just go in all four directions basically, right? So if we go here, we'll get OE. If we go this way, we'll get OA, right? Et cetera, et cetera. We could, possibly make a word like this, OAAN. Or we could make a word like this, OATH, and this happens to be a word in our list of words. So we would say, okay, OATH, this is a word, so this is going to be added to our solution set, so it's going to go in the output. So a very brute force approach would be, for every single word, we're going to run a depth first search starting at every single position and check, okay, could we make the word oath starting from here? Could we make the word oath starting from here, et cetera, until we get, all the way to the bottom of the grid. And we have run a depth first search on every single position. Now that's not going to be super efficient, right? And then we're going to have to do the exact same thing for the next word P, right? Because maybe this word could exist, so we'd have to brute force check every single position, et cetera, et cetera, et cetera. And one way to analyze the time complexity of that would be something like worst case 4, and 4 because that's the number of directions from any position we could go in 4 directions. Now we can't revisit the same position twice, of course, so basically the length of our depth first search is going to be the dimensions of the board. Let's call that M by N. Right, so that's how much one DFS would be, and we're going to be doing a DFS starting at every single position, so it's going to be something like M by N to the power, or M by N multiplied by 4 to the power of Mn, and we're going to be doing this for every single word. So basically, let's say W is the number of words, so this is going to be super inefficient. Now there is a way basically where we can make this more efficient, where we can get rid of this constant W. Basically, the solution is going to be, we're only going to have to run DFS starting from each position a single time, because as we're checking, what are all the words we can create starting at this position, right? Starting at this character A. What are all the words that we could create? Now, the main idea that we're going to be doing, instead of just checking a single word at a time, like running DFS on here just to check if this word exists, let's check simultaneously. Let's check all the words in our set, which of them can be created starting at this position. So that's the idea we're going to be using, and we're going to be using a data structure, which is going to be very useful for it, because what we're going to notice is we can check all words starting at here based on the prefix, right? So clearly here, we only want words starting with the letter A, right? So the prefix is going to be A. And what kind of data structure can help us organize these words based on their prefix? Guess what? Either you have heard of this data structure before or you haven't. If you haven't heard of this data structure, then you probably don't have a chance of solving this problem in the optimal way. So I would learn what this data structure is first, but if you do already know it, the solution is actually not too bad to implement. So the data structure we're going to be using is a trie, aka a prefix tree, which is going to help us organize these words based on their prefixes. So let's say we had a pretty small grid and we had a pretty small list of words. The words are app, ape, and ace. So we want to know which of these words can be found inside of this grid. Now let's use the idea of prefixes that I mentioned. So let's say we're going to start our DFS here, right? So this is the first position we're going to be at, and we can't revisit this position twice. Makes sense so far. So far we have a single character, right? We have found the character A, right? So we can basically, we want to know all the words that we could create starting at this position, DFS from here. And of course, then we're going to repeat that by doing a DFS from here, here, and here. But so far we're only starting here. And of our entire list of words, we want to know which one of them have a prefix of A, because if we had a word such as bat, then we'd say, okay, bat does not start with an A. So basically we don't even have to consider that, right? We don't have to run a DFS on here searching for the word bat. It doesn't even exist in this position. Right? The letter B does not start here. So what we're going to have to do is basically go through every single word. This word starts with an A. This word starts with an A. This word starts with an A. So potentially so far, all of the words could be found starting at this position, right? So we haven't eliminated any of these just yet. So now let's say we go down first, right? Of course, if we go up, that's out of bounds. So, we're just going to return there because we're going to see, okay, it ended with the word A. A does not exist in our list of words, so of course we're not going to do that. Of course, if we went left, that also would not work, but we can go down. So let's start going down first. So we add a P to our word so far. So far we have AP. So then again, we're gonna have to just go through every single word, check, okay, does this start with AP? Yes. Does this start with AP? Yes. Does this start with AP? No. So we don't want to consider this word anymore, right? But as you can see, this is gonna get kind of complicated, right? We're having to go through the list of words every single time. That's not really helping us out in terms of efficiency. A more intuitive way would be if we could check the prefixes of these words more easily. And of course, we know a data structure, prefix tree, is exactly what that is for. So basically what a prefix tree is going to be, it's going to be, every single character is going to be a node. So one node is going to be A, and we're just going to take these words and add them to our prefix tree. So we want all words starting with the character A to go here, right? So let's add childs of these. So what characters come after A? Of course, we have a P and then we have a C. So all words that start with AP are going to go down here, and all words that start with AC are going to go down here. And how many different words do we have that start with AP? We have app and we have ape. And all words that start with AC is just one word, ace. So do you see how this tree is organizing these words based on the prefixes? So now we started at A, right? We want all words that start at A. So this is where we're going to be at so far. And we see that, of course, there are 3 words that start with A. And by the way, let's say AP, this is not a word, even though it is a path in our trie, because basically, let's just say we call these 3 leaf nodes happen to be the end of words. It's possible that we could have a word AP, but in this case, we don't up here, right? We don't have AP, so this node is not going to be marked as the end of a word. So only these 3 are marked as end of words. But so now when we go down in this direction, we go to a P, all we're going to do from this position is check, does this have a child P? If it does, we're going to say, okay, let's go there. So now this is going to be all words that potentially start with AP, so this prefix. Now, if we did not have a P, right, then we would say, okay, we went down here, AP. We don't have any words that start with AP. So in that case, we would just return. That's our base case, right? If we didn't have any words with a prefix of AP, which we could check pretty easily with this prefix tree, we wouldn't want to continue going down this direction. So you can see that we're making things a lot more efficient for us using this trie. So now from P, we can't go down, that's out of bounds. We can't go left, we can't go up because we already visited that position. So we can go right, which is going to add the character E. So from here, from this P, we want to check, do we have a child E? Well, this is not the E, this is though, right? Okay, so So far, we did find a path in our prefix tree. Now, let's check. Is this the end of a word? Since it's marked purple, that's what I'm just indicating. So yes, this is the end of a word. Therefore, we found a single word down this path that we were maintaining called A, P, E. That, yes, you can see it's found in our list of words. So therefore, we found one word that we can make from this grid that, can be found basically. So we're going to add ape to our results. Now from here, we would want to continue. Now we can't go right, we can't go down, we can't go left because we already visited there. So we would go up. So we'd say, okay, add a C, right? So from here, APE, and then we add a C. Does this word exist? Well, this does not have a child of C. So of course we can't do that. And that makes sense because this word APEC does not exist in our input list of words. So therefore, at this point, we would return because we don't even have any words that start with this prefix. So far we did find one word, ape. Now, when we started here, the first direction we went was down, but it's possible we could also go right. So let's do that. So now we have AC. So we started here. We checked, does this have a child C? Yes, it does. It's over here, right? So now we can't go right. We can't go up. We can't go back left. So now we go down. ACE. Do we have a E child under this C? Yes, we do. And this is the end of a word, right? It exists in our list of input words. So now we found another word, ace, and then we would continue from our grid in the only position we can go to, which is the P, right? So we'd add a P. We'd say, okay, does this E have a child P? It does not. So therefore we can't continue. So that's going to be our base case, but it's okay because we at least found one word. So we can go ahead and add that to our list of words, ape and ace. So now is going to be the easy part. So we started our DFS from this position. Now let's start the DFS from C. So we look in our prefix tree. We do have a prefix starting at A. Do we have a prefix starting at C? We don't. So immediately we can say, okay, we know for sure none of our words start with the character C. We didn't have to run through the list of words to do that. We just did that in an O of 1 operation. We just checked, does our root node have a child C? It does not. So therefore, none of the words start with a C. So we don't even have to continue the DFS from this position. And you can tell that's the same is going to happen for the character E. None of the words start with E. We don't have an E root node in our prefix tree. Similarly, P, we don't have any root node P. None of the words start with P. So we're not going to find any additional words in this grid. We only found 2 words, ape and ace. We found ape and ace. We did not find app. So we're going to return these 2 words as a list. So once you kind of understand that this problem can be solved with a prefix tree, and you know how to implement a prefix tree, and you know how to implement backtracking DFS, which you can learn from Word Search 1, this problem is not too difficult. So now let's write the code. So the first thing I want to do is actually implement a trie node class, or a trie class basically. And so in the constructor of this, if you have written a trie before, you'll know that there are mainly 2 things that we worry about for a trie node, and that is its list of children. So that's going to be one member variable for this class, a list of children. Now you could use a list. In this case, all characters I think are going to be from lowercase a to z, but a more generic way to handle it is just using a hash map. So the key is going to be the character, and the value in this hash map is going to be the child node, the child trie node. And also for each node, you want to be able to mark if it is the end of a word or not. So one member variable for is word, it's going to be a Boolean. Initially, we can set it to false. Now to our trie, we are going to want to add words to it. So let's define one function, add word. And this is really going to be the only function. So we'll be passed in a string, a word, and we just want to add that word to our trie. So let's get our current pointer to be at the root node, which is just the self node. And then we're going to go character by character in this word and just start adding them. Now it's possible that the character might not exist in our trie node. If it does not exist, so if C not in current.children, if this character does not exist, then we're going to obviously have to insert it. So current.children. At character C, we want to create a trie node for this particular character. If it already exists, then we're going to skip this if statement, and simply we're just going to move our current pointer to that position. So current.children at character C. So that's the trie node that we want. And at the end, all we have to do is return the current pointer. Or actually not return the current pointer. At the end, we have to mark that this is now going to be the end of the word. So the last character that we ended at, current, is word, we want to set that to true when we insert a word. Now, the reason we're not going to define a search function like searching a word in this try node is because we're going to be doing that simultaneously as we do our depth first search on the board. So now let's start getting into the DFS. Or actually, the first thing we're going to want to do is create a root try node. So let's create a try node with the class that we just defined. And for every word that we're given in the input, so for W in the list of words, we just want to go ahead and take each word and add it to our try. So root.add word W. And now we can start going ahead and doing the depth first search. So first I like to do is get the dimensions of the board. So rows and columns, we can get the length of the board. We know for sure that the board is going to be non-empty and the list of words is going to be non-empty as well. They do tell us that in the problem description. Now I'm going to create two sets, result and visit. So result is going to be the set of words. It's possible we could visit the same word twice inside of our board, so we don't want to have to return duplicates. And the visit set is pretty self-explanatory. When we run a DFS on the board, we don't want to get stuck in like an infinite loop, or mainly we don't want to repeat the same character twice. We're not allowed to do that. So once we have those defined, we are going to define a DFS recursive function. We're going to be going through every position. So we want to pass in the coordinates, row, column as the coordinates. We want to pass in the current node that we're at in our try, depending on what characters we've already visited before. And we also want to pass in what is the word so far. So for example, we visited two characters, AC. We want that to be stored in this word variable. And of course, if the node that we're visiting happens to be the end of a word, what we're going to do is just take that word and add it to our result, which is out here. We don't have to pass it into every recursive call. So for this DFS, let's go ahead and define the base cases. So of course, if we go out of bounds, row is less than 0, or column is less than 0, or row is too big, meaning it's the number of rows, or column is too big, meaning it's the number of columns, or maybe this position row column is already been visited. So if it's already in visit, then we're going to return. Or maybe the character that we're at, for example, board at position row column, maybe this character is not even in our try. Maybe it's in bounds, right? But it's not even in our try at the current position that we're at in our try node, right? Meaning this character is not in node.children, right? If it's not in the children of the current node that we're visiting, that means this character doesn't exist in our try. Therefore, it's not one of the words that we were given in our input list of words. So if any of these are true, then we're going to return. That's our base case. If that's not true, first thing we want to do is make sure we mark this position as visited. And after we're done, the last thing we do before we return is we're going to have to mark this as unvisited. Basically, since this is backtracking, we can't visit the same one twice. But once we're no longer done visiting it, after we return, then we can go ahead and remove this position from being visited. So since we got to a new character, we want to update some variables. So we want to update node. So node is going to be set to node.children of the current character that we just visited, which is board at position RC. So we're updating the node because we know that that node does exist. And we're updating the word, right? So we're taking the current word, adding to it the new character that we just reached, board at RC. And before we do the recursive case again, before we look at the neighboring positions, we do want to check, is this the end of a word? So we can check that based on our node. So if node is word is true, then of course we can take our result and add to it the word that we just built, right? The string itself, not the node. We're not going to add the node to result. We're going to add the string word. So this is just basically, checking if it actually is a word in our list of words, and we're, doing some bookkeeping here. And once that is done, we can go ahead and actually do our recursive case. You could write it with a loop, but I like to be lazy, and I think it's pretty okay to just copy and paste DFS 4 times. So we're going to pass in the coordinates, and we're going to pass in the node, and we're going to pass in the word that so far we have built. So let's just copy and paste this 4 times, going in each of the 4 directions, up, down, left, right. So all that, we have defined our DFS function, about 15 lines of code. So remember, what we actually wanted to do with that DFS is go through every single position, every single starting position in the grid. So I'm going to do a quick 2D loop or quick nested loop on the entire grid and call DFS from each starting position in the grid. Now for node, what are we going to pass in? We're going to pass in our root node that we defined up above. And for the word, initially, it's going to be empty, right? So that's what we're going to pass in for the word. Once that is all said and done, we want to return our result. But don't forget, our result is a set to eliminate duplicates. We can cast it into a list pretty easily in Python. So that's what I'm going to do. As you can see, this is the entire code. So this is the entire code in all of its glory. So this, you can see that this solution does work. Once or twice, it actually did give me time limit expire. I think there is a slight optimization that you can make to this problem. I don't think it actually improves the overall time complexity. But once you find a word in the trie, basically what you can do is actually remove that. If it's a leaf node, you can remove that from the trie, because you don't have to search for the same word twice. That's a slight optimization that you can make, but I think this solution is mainly good enough, and it's too big to even fit on the screen. That's how you know this is a hard problem. No matter what you do, it's going to be a lot of code that you have to write. But I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Thanks for watching.